Okay, so just to make sure you guys can see this, right? And you guys can hear me all right with nothing like no background noise or anything. I'm gonna wait for a response. Since if something is wrong with the thing and okay, thank you. So let's get started. So this is a group theory, except it's not the kind of perspective that Mr. Lee usually teaches. It's more of abstract and more like teaching about like the actual theory of it and less about its applications to things like Olympiads. So what is a group? A group is a set of terms or values, G, coupled with an operation that satisfies a set of axioms. So the first one is closure. And for A, B that are in G, A times B is in G. So times is the operation. So essentially what that means is, for example, if the operation is plus, and you have like a bunch of numbers, just integers, then it would be A plus B equals is in G. So identity, there exists an identity, we're going to call it E, that is in G. And for any A times E is equal to E times A, which is equal to A. And then for inverse, which is the third one, for every A that's in G, there exists an A to the minus 1, or the inverse of A, such that A times the inverse of A is the inverse of A times A, which is equal to E, which is, again, E is the identity. And then associativity, A times B times C is equal to A times B times C, regardless of where you put the parentheses. So if a group G is commutative, like A times B is equal to B times A, then G is called abelian. So let's go into some examples because, I mean, that's a lot of information to take in. So example 1, the set of integers over addition. This is an abelian group because A plus B is an integer, so it's part of the set of integers. So, and we can set the identity E to 0 because A plus 0 equals 0 plus A is equal to A. The inverse of A is minus A because minus A plus A is equal to A plus minus A equals 0. And then A plus B plus C is, I mean, I'm sure you all heard of the associative property for addition. So that is pretty much the same thing as the rule of associativity here. And lastly, A plus B equals B plus A, which means that it's abelian. So another example is pretty similar. Z over 6Z, which pretty much means that the integer is mod 6. So the set is only like composed of 0, 1, 2, 3, 4, 5. I mean, we'll go over this particular set, or types of sets, a little bit more later. But the set is only composed of those 6 elements, where that number in brackets means the equivalent set of n, or the set of all integers congruent to n mod 6. For example, if we have the equivalent set of 2, that's going to be 2, 8, 14, 20, and also -4, -10, and so on. So the proof is similar to example 1 in that, I mean, we set E to the equivalent set of 0. If we add the 2 equivalent sets, it's going to be another equivalent set. For example, if we add 2 and 5, that's, I mean, you might think that that's 7, but 7, the equivalent set of 7 is the same as the equivalent set of 1, since they're the same mod 6. And of course, the associative property still is upheld. The inverse of A is minus A. In this case, the equivalent set of 1 matches with 5, 2 matches with 4, and 3 matches with itself. And so does 0 match with itself, pretty much. And also, yeah, that's pretty much the 4 rules. So problem 1, find a group that isn't abelian. So I think with the problems, the plan is just, I'm just going to give you guys maybe 2 or 3 minutes, depending on like what the problem is, in order to solve it. If I'll solve it, and if someone has a solution, or then you can put it in the chat or speak up or something like that, because if no one solves the problem, then it's going to be a little bit awkward. And if you want a hint, I can always give you one. All right, I mean, you guys probably thought of it a little bit. I'm just going to assume that you are ready to move on. So, this take okay, it's called S3, which is defined as the rotational and reflectional symmetries of an equilateral triangle. So, for example, if we have this triangle right here, we have 1 at the top, 2 on the left, and 3 on the right. So, we also just define R is rotating the triangle clockwise. So that would be, now let me get ready, kind of, I don't have a mouse, so don't expect good directions. So when one clockwise, which would be here, so now this becomes 2, this becomes 1, and this becomes 3. And S is the reflection across the vertical line of symmetry. So we're talking about this line here. So if we use just S, then this would be 3, this would be 2, and then this 1 would stay as 1. So this is one of the simpler solutions to the problem that I gave you before, so what I mean by it's not abelian is that SR is not really equal to R. Wait, hold on. Yeah, SR isn't equal to RS because SR takes, you know what, I should probably not, yeah, I'm kind of skipping steps. So the 6 elements of S3 are E, which is the identity, which is do nothing transformation, just keep it the same, R squared, S, SR, and SR squared. So an important thing to know about this is that multiplication is right to left. This is very important because a lot of the time, if you're doing multiplication in the wrong order, it's pretty obvious that you can mess up because in this case, it's not abelian, so it's not like you can just have, you can just ignore order altogether. So we can draw a multiplication table multiplying all the combinations of these events. For example, S times R squared rotates the triangle 240 degrees clockwise, then reflects it. So let's see what happens to 1. So 1 goes to here, and then reflects it to here. So 3 becomes 1. And what happens to 2 is that it gets rotated and back here. So 2 stays at 2. And then 3 goes to 1. And this can also be expressed as SR. Because, shoot, I think no, it's SR squared is equal to RS. So I made a mistake here. This is actually supposed to be RS, where S comes first. So what I mean by that is the 3 goes here first, and then it gets rotated up here. 2, reflects here and then rotates there. And then 1 rotates, it's reflected, which does nothing, and then rotates here. You see what I mean? So another example, SR squared times E is equal to SR squared by the rule of identity. So E doesn't change anything, so we can pretty much just remove it when we're multiplying stuff together. So normally I would ask you guys to fill out the multiplication table, but since we're a little bit short on time here, we only have an hour. I'll just say the multiplication table here. It looks like this. And what I mean by it's not abelian is that, oh shoot, yeah, that's what I mean when I say I can't really draw on the computer. So SR, so the right is S, so this is what goes first. So if you reflect and then rotate, you get something different from if you rotate and then reflect. So if you just take just like 1 as an example, if you reflect first and then rotate, it goes over here. But if you rotate and then reflect, then 1 goes over here. So it can be different depending on order. So another important thing to remember if you were to fill out this multiplication table is that R cubed cancels to E as well as S squared. So, but what I mean is that if you rotate 120 degrees 3 times, that's rotating 360 degrees. So that does nothing. And if you reflect twice, then it's also, it takes you back to the original state. So now we're going to talk about subgroups. So a subgroup H of a group G is something defined by the same rules as a normal group. The only difference is that as a subgroup of G, H has to be contained inside G. So for example, the integers mod 6 are contained in all of the integers, which is pretty obvious because 0 through 5 is a subset of all the integers. So the identity set, which is just E, is always a subgroup of any G, since if you want, you can check it on your own, but E is a group. And plus, since every group has an identity, then, it's part of that group. So G is also always a subgroup of G, because if G is a group, then G is a group, and it's also contained inside itself. So an important thing to note is that E is always in the subgroup of G, as since subgroups preserve the, I made a grammar mistake here, but E is always in the subgroup of G, as subgroups preserve the operation and thus the inverse. So, for example, this subgroup and this subgroup have the same identity, which is 0, or the equivalent set of 0. And of course, it's pretty obvious that every subgroup has to have an inverse because every group has to have an inverse. So find all subgroups H of Z over 6Z plus. So we can prove here with the same strategies that I think I might have this. Okay, whatever. We can prove, so E, Z over 2Z, Z over 3Z, and Z over 6Z are all subgroups. So, for example, since we have 0 through 5, we'll start with different cases, because I think I forgot to mention Lagrange's theorem, but I'll say it here right now. So Lagrange's theorem basically means that the order of H, or the number of elements in it, is always divisible by the order of G. And again, since we were low on time, the proof is left as an exercise. I mean, I can just say that about anything, but really. So since the order of this is 6, all subgroups have to have either 1, 2, 3, or 6 elements. So we'll start with 1 element. The only possible thing is E, since E must be in the subgroup. If we go for 2, E and 3 are the 0 and 3, and 0 is E, and 3 are really the only choices. Since, well, what happens when you, like, if it was any other number n, then n plus n would have to either equal itself or 0. And n plus n can't equal itself unless it's 0, and n plus n can't equal 0 unless it's 0 or 3. Since, again, make sure to follow the mods. And 0, 3 is different from 0, 2z, since 0, 2z, 0, 1, but they're isomorphic, which we'll go over later. Basically, what that means is that these are pretty much the same group, because this is mod 6, and this is mod 2. Wow. They're both they're pretty much the same group. If, like, this is just this if you multiply every number in there by 3. Similarly, we can figure out that z over 3z is a subgroup, and z over 6z is the same as g, so it's obviously also a subgroup. So proving that they're the only ones is not hard either. And again, Lagrange's theorem is how we can prove that there can't be anything with 1, 4, or 5 not 1, but 4 or 5 elements, and that these are the only ones with each of 1, 2, 3, and 6 elements. Using Lagrange, this is kind of just what we went over. So problem 3. Find all subgroups H of z over nz plus. So I'll give you 3 minutes for this, till 5:23. Also, yeah, reminder that if anything doesn't make sense, or if I'm going too quickly, or if I'm going too slowly, then you can always mention it. Like, whether it's in person or chat, you can direct message me, whatever. And I'll go over the solution to this. All right, so again, I'm just going to assume that you guys are ready to see the solution. If anyone disagrees with me, then be sure to mention it in like the next 10 seconds. Otherwise, I'm going to spoil the solution for you, and that would kind of suck. All right, again, no one's saying anything, so I'll just go forward. So the solution to this should be that it's just z over, which letter do I use? How about q Z for any Q that divides Z. And of course, you also have to tack on just the E. So the reason why this is because by Lagrange, we know that the number of elements in the subgroup must divide n. So it must be a factor of n. And then we can sort of deduce using the same sort of technique that it must be this kind of form because of the closure rule. Because by the closure rule, two elements in that subgroup must add to another element in the subgroup. So if we have one element, let's say, I don't know, Z over 5,000 Z, we have 5. 5 is our smallest element. Well, 5 added to all these other elements must equal the next element. So 5 plus 5 means that there must exist a 10, must exist a 15, must exist 20, all until we get to 5,000, which is just 0. And then it sort of just loops around, and 5 plus 0 equals to 5. And if you were to add any number that's not divisible by 5 here, then it wouldn't work. Unless it was smaller than 5, then you would have to add more numbers. Well, if you would have to add more numbers because, how do I explain? Because then, if you added like a 3, then 3 plus 5 is equals 8. 8 would have to be in there. 3 plus 8 equals 11. 11 would have to be in there. And suddenly you just have all the numbers. All the numbers from 1 to 5,000. So we can now move on to the slightly larger task of finding the subgroups of just the set of integers itself, which is Z. Okay, so we start by setting the smallest positive number in H as S. Because if there are no positive numbers in H, then it cannot be a subgroup, but with one exception. Why, and what is that exception? Well, why is because if there are no positive numbers in H, every number must be either negative or 0. Wait. Yeah. And actually, you can have. Wait. I'm confused. No, yeah, because you have to have an inverse. And I kind of forgot about that. But if you have no positive numbers in H, then there must be an inverse for all these negative numbers. And that's not possible unless you have a positive number. So now and the exception here is just E itself. Since E is its own inverse, it doesn't need, another number to be added to be an inverse. So now we know that H must be as Z, which includes all positive, negative, and 0 multiples of S. Because the existence of S in H implies 2S, 3S, and so on. By inverses, this also implies the existence of minus S, minus 2S, minus 3S. And of course, you can't add any number smaller than S, and you can't add any numbers larger than S without, giving way to another number that's smaller than S. Because the existence of like 11, when S equals 4, makes a need for an existence of 7, and thus 3, and 3 is smaller than 4, which is a contradiction. So now this proof isn't complete. So finish the proof by showing that the smallest possible numbers of is S. Oh wait, I kind of spoiled it. But the only possible numbers of H are multiples of S. Then conclude by stating that the only possible subgroups of Z are N, Z, or 0. So actually, I kind of lied to you earlier when I was saying that Z over 6Z was a subgroup of the integers, because this equivalence class of 0 isn't really equivalent to 0. But yeah, and it's not isomorphic to say just a normal set of integers 0 to 5. But I think you guys all understand this. So now homomorphisms and isomorphisms. So what a the homomorphism. H is like just the name of the homomorphism. G and H are different groups, and it occurs when H of A is equal times H of B is equal to H A times B for A, B, which are part of G. So what we're talking about, H of A is going to be part of H, when A itself is just part of G. Proof that for a homomorphism, H and G to H of EG is equal to E of H, where EG represents the identity of G. Also prove that H A to the minus 1 is equal to H A to the 1. So, to the minus 1, or the inverse. So, for the first one, we have H of EG, H of the identity of G, times H to the B is equal to H EG times B, except EG times B is just B here. So H of EG times H of B is equal to H of B. And since these are part of H, this must be the inverse of H, which is EH. Now for this, H to the A to the minus 1 times H of A is equal to H times E to the G. And we know that this is E of H. So now we know that these two are inverses because they multiply to EH. So an isomorphism is basically just a fancy homomorphism. G to H occurs when an H is a homomorphism and a bijection. So bijection is, I'm sure you guys know what it is. It's pretty much when two sets are one-to-one. They have like one-to-one pairing. And basically this means that each element in G has a unique pairing with an element in H. Prove that the set of clockwise rotation. So, I mean, some people just treat it like two isomorphic groups are the same group. And they pretty much are, except for maybe a few, technicalities and just the name of the groups. So prove that the clockwise rotational symmetries of nonagon are isomorphic to Z over 9Z. So if we do some testing, we'll see that this corresponds to that, this corresponds to this corresponds to that, and then we can sort of make a conjecture that rotation by 2n pi over 9 when we're talking about radians. Or if you want to talk about degrees, it would be 40n. We can make a conjecture that rotation by that amount corresponds to n, like the equivalent set of n in mod 9. This is easy to prove using addition, and the fact that we can subtract 2 pi and 9 to yield the same result. So we can generalize this to 2 pi over n and z over 9z for n. So pretty much what that means is that if this and this play the same role in the group, so each clockwise rotational symmetry of a nonagon has its own, sort of counterpart in z over 9z, which they both have the exact same effect. So for example, if I have it's kind of like equilateral, congruent triangles. If I have like a triangle here, then I have a triangle over here, and this is 1, 2, 3. This is 1, 2, 3. I should have said ABC, but it's fine. These ones sort of match up. These twos match up, and these threes match up because they're counterparts in the congruence. So it's just like this with each member of the group. So now we're faced with an interesting problem. Is classify every finite group up to isomorphism. So this is this is an impossible problem so far. No one has done any, no one has come out with a solution. And that's because it's very large. And, and it's difficult. So basically that's what we'll be working toward today. We won't get there, obviously, but we can investigate to see how far we can go. But for this, at first, we'll have to learn simple normal groups, and then, what are they called? dude, okay, I'm just gonna scroll down. They're called the composition series. I probably should have practiced doing the lecture. So simple groups and normal groups. So stating that one group is a normal subgroup of another, or N is just this triangle to G, means that for all N in N and G in G, I mean lowercase g in uppercase G, lowercase g, the inverse of that, times N times G is in N. So, I mean, just to clarify, remember that multiplication is right to left. So G comes first, and then N, and then the inverse of G. Also remember that this isn't just multiplication in the standard sense, like 2 times 4 is equal to 8. It's more of a composition thing, like what you would see in composition functions. So find a subgroup that is normal to Z over 24Z. So there are many possible answers to this question, but we can take Z over 4Z as an example. So in this case, this refers to 0, 6, 12, and 18. And that's just for ease of access. They could technically be 1, 2, and 3, but like it's isomorphic to 0, 6, 12, and 18, which like lines up per se with Z over 24Z. So it's just a lot easier to do the calculations in this way. So obviously, I mean, this is just a plus, right? I mean, since we know that these are abelian, we can just switch them around, and you know, if we have the minus G and G right next to each other, those cancel, and you get N is equal to N, which is obviously in Z over 4Z because it's just the same. So the reason why this was so easy is because G is abelian. If G is abelian, every subgroup is normal to G, since we can just rearrange minus G and N and then cancel and have N equals to N. So also notice that G is normal to G and E is normal to G. I mean, that's pretty obvious because by closure, if these are all members of G, this must be a member of G. And E is just, I mean, the E's literally do nothing. So we're just left with N equals to N. So what if G and E are the only normal subgroups of G? Then G is called simple. So for example 7, I want to prove that Z over PZ is simple if P is a prime number. So we've already proved that the only subgroups of Z over NZ are Z over QZ if Q is the factor of N or E. So I mean, G and E are pretty much like the only subgroups, period, of G, as long as G is Z over PZ. Therefore, if N equals to P, its only subgroups are E and itself. Since it's abelian, these are both normal subgroups. And plus, I mean, we know that from this. So the subgroup is therefore simple. There are actually a lot of simple groups out there. In total, they can be classified into 16 total groups. So I think Z over PZ is one of them. And there are many groups defined by various things like calculus and geometry. The most interesting of these is probably the sporadic groups, named so because they don't fit into any other category. And sporadic groups have like a variety of sizes. The smallest one, I think, is in the thousands. But the largest and most famous of the sporadic groups, called the Munster Group, M, has order or total elements 2 to the 46 times 3 to the 20 times 5 to the 9 times 7 to the 6 times 11 squared times 13 cubed times 17 times 19 times 23 times 29 times 31 times 41 times 47 times 59 times 71. And that, I mean, the reason why I wrote this out is because just to show that it's not like it's, I mean, it seems completely random, and also because of something that we're going to look at later. And this is greater than 8 times 10 to the 53 elements. And this is a simple group, mind you. So E and itself are literally the only two groups, the only two subgroups of this giant group that are normal to it. And, you know, it's kind of odd that, you know, random messes like this can be generated from just a set of a few simple rules that look like they could just, be obeyed by a lot of simple, or by simple I mean not that kind of simple, but relatively benign groups. So as for all finite groups, I mean, this is just all the simple groups. So for all finite groups, how are we going to construct them from, just a bunch of simple groups? Because, I mean, there's pretty much no tie so far. But in fact, there is, and it's called group composition. So a composition series of a group G is a way to arrange groups G0, G1, G2, all the way to Gn, where we have G0, which is equal to E, Gn, which is equal to G. And all of the quotients Gn over Gn minus 1 are simple groups. So if we only have 3, let's say G0, G1, G2, G3, n equals 3, then all of the quotients G3 over G2, G2 over G1, and G1 over 0 are simple groups. For example, for G equals to Z over 900Z, one possible series is E, Z over 2Z, Z over 6Z, Z over 18Z, Z over 90Z, Z over 450Z, and Z over 900Z, with quotients Z over 2Z. See, this is just 2. So what I mean by quotients are, it's not just about the order, because this is order 900, this is order 450, that's order 2. I mean, it's not always going to be like that, since this is just like a special case where we have the pretty simple mod groups. But what I mean by quotients is that if you multiply this, like every element times here is equal to this. So what it means is that if we have 0 to 449, we can multiply that by 2. So we have 0 to 449. It's spread out. So, I mean, if you multiply that by 2, you get 0 to 998. All the even numbers from 0 to 998, which is exactly the same as this. But you can also add like a copy of this, which is shifted up 1. So it's 1 to not 998, 898. And then 1 to 899. And if you add those two groups together, you have a total of all of the numbers from 0 to 899. So again, this is just odd, and this is just even. And if you add the two together, then you get Z over 900Z. So the other quotients are Z over 3Z, Z over 3Z, Z over 5Z, Z over 5Z, and Z over 2Z. I don't think, oh, actually, I went the wrong way. This is 2, 3, 3, 5, 5, and 2. And for the Munster group M, since it's simple, it would literally just be E and M with the quotient M, which is a simple group. So that's how it is for all simple groups. And I just use it as an example because, well, it seems fitting. Prove that every group G has at least one way to arrange a composition series. So the proof goes something like this. By definition, if G is simple, then it is composition series E, G, and E is normal to G. If G is not simple, then there's another group besides E and G that is normal to G. So if G is not simple, like up here, Z over 900Z, there's another group besides E and G that's normal to G. For example, I mean, we showed you that Z over 450Z is normal to 900. So since G is finite, we can also assume that there is one with maximum order M. So by maximum order, I'm talking about the group that is normal G with the maximum order. So again, Z over 450Z is M in this case, since there is nothing higher than 450 order that is normal to this. And again, you can just check with Lagrange. So since we know that this is maximum order, G over M is simple. And because if it wasn't simple, then there would be another group in between, and you could just divide by that group and then another group, and then that contradicts you, because if you like the intermediate step of dividing in by that group makes it larger than M. So therefore, we can start using induction. So the base case is just simple groups. Inductive, I mean, all of these groups have composition theories as just E in itself. Inductive step, if a group A has a composition series, then A times simple group also has one. Since every group can be expressed as M times simple group, then since these groups are finite, we can apply this rule from E all the way to M and then G by multiplying by one simple group each time. This is because simple groups must have 2 elements or more, so only a finite amount of simple groups can be part of a finite group. So if we have a group with, let's say, 100,000, yeah, again, handwriting thing, 100,000 elements, you can't just keep dividing by 1 to get the same thing and never finish with this composition series per se, because simple groups always have 2 elements or more, unless you have E. But E, again, we ruled out E by saying that M does not include E and G. Group has a composition series, we can construct all possible finite groups out of simple groups. This has never been done yet, and most people believe that in our current state of technology, no such classifications are plausible. So technically, we can say that all groups are composed out of simple groups and then just leave it there. But just finding all the groups is pretty much impossible because there's just too many cases that you have to consider with infinite amounts, because the 16, I mean, when I say 16 groups of simple groups, we're talking about 16 groups of, and some of them are infinite. So there's an infinite amount of simple groups. So there's, I don't know whether it would be right to say a larger infinite number of just groups, finite groups in general that are just harder to classify. So now we have exercises. So some of these are most of these are probably pretty easy, but considering the pace that we went through class at, I wouldn't be surprised if you would find these challenging. So if there are any, okay, I'm going to zoom out a little bit. If there are any questions or if you want to share your answer, then be sure to tell me about it, because I did go through that rather quickly. So if you have questions about the topic, questions about the exercises, questions about anything really, or if you have an answer that you'd like to share, just put it in the chat or say it normally. And I assume all of you guys have the PDF, so I'm just going to stop sharing.